Hey kids, Professor Science here. I'm gonna go ahead and drop the nasally voice and put away my glasses. They're just plastic lenses anyway. And I wanted to show you guys something that I found that was really interesting that as far as I can tell, no one's kind of come across this information yet. So, hey, if you want to write a doctoral thesis, here's one free on you from Professor Science. No one else knows about it, so they won't know. You can give the prof some creds after you make $1 million. I'm just kidding. Anyway, the what I found here is in the Space Weather Journal. There was a hypothesis put forth by a couple of Japanese scientists, and they were basically saying the red auras in the Kyoto region in the 1770s were a sign of a massive solar flare way bigger than that of the Carrington event. And it is very strange to have big red auras at that longitude, in that area of the world. But there's actually a lot more plausible explanation, and we'll go into that at the end. But the interesting thing that's even more interesting than that is the relation of solar flaring cycles and high ejection cycles with the magnetic derivation of the poles, basically the magnetic variance, the magnetic drift, if you will, and the direction of said drift. Now, that being the case, let's go ahead and pull up the historical map of how the poles have been migrating. And this is from, around just before the 1600s. And this is a lot of corroborated data based on a lot of old sea mariners' data gathered. I mean, the East India Company, they kept meticulous records. A lot of, people who didn't want to die at sea often paid very close attention to their instruments. And with that, we have a wealth of logs and information in which can be compiled into where magnetic north was, and where it was moving and the rate at which it moved. So what you're looking at here is this blue line here, the blue dots. Let's go ahead and zoom in so you can kind of see. The blue dots would represent that pre-1590 era, and then it basically is going like that, and you kind of get the speed by how the spacing of the dots are. We'll go into a lot of that later if you'd like another talk on that. But essentially, what we find is that the correlation with where north was, where it was observed, and then all of a sudden you see right here, boom, and it shoots back this way. Now, 1631. What happened in 1631? Well, as we know from solar flares, sunspot cycles, is that at the low regions of flares is when you get the massive ejecta type flares. It's simple surface physics of the viscosity of the sun itself. So when you're at a very high flaring activity, you see lots of little flares all over. Imagine, if you will, a pot of spaghetti sauce that is well heated and well stirred, and you just see it simmering on the stove, and it might splatter out a little bit, but the viscosity is so great that it allows it to freely kind of move, and none of the gas pockets can really build up and blow out large amount of matter, i.e. spaghetti sauce or plasma, on your kitchen. I hope it's spaghetti sauce for your sake. That being said, if you look at the low periods of the sun, what you're going to find is that the viscosity gets real low and slow, and the viscosity then allows the buildup of huge gas pressure areas where, when they burst forth, they might eject trillions of tons of iron at your little sphere you happen to be traveling on in the solar system. That being the case, you can basically count on the ramping up of these sunspot cycles, which are on 11-year cycles, 206-year cycles, and I would believe around 12,000.5 year cycles, but that's a whole nother video. That being said, we can actually see, and this is kind of the interesting correlation that I've discovered here in the data, is that each directional shift in the magnetic drift, so to speak, is preceded or during one of these very low sunspot cycles, which means the Earth was more than likely blasted with a very large amount of matter. I mean, literally trillions of tons of matter. In the case of, Carrington event type eruptions, who knows? Quadrillions, sextillions. You could put whatever ridiculous number you want almost, because there was really no way of measuring it back then. But what we can measure is that movement. And that's where I want to show the correlation I've discovered. Now, so here we go in the 1631 era. As you can see, very low sunspot cycle, and then the ramping up. Well, the ramping up, if it were up to me to decide, I bet it's probably something to do with essentially like a sector boundary crossing event that occurs in the Milky Way on a much minimum cycles and then grand cycles, just like the minimums and the grands of the solar cycle itself. There's a super grand that actually correlates to the grand cycle would correlate to one of the cycles from the center of the Milky Way, and then the other would correlate with the larger cycles. Obviously, microcosm, macrocosm, things influencing other things. But I digress. What we have here is the historical data from 1631, corroborated and correlated perfectly with that low period of low viscosity and higher ejecta matter. And now let's go ahead and go to the next big turn, which is 1729. And so in 1729, we have, going one direction, heading south, and then switching direction once again. And let's go to the 1729 there at the low sunspot cycle, and then the big ramp up. So obviously another high ejecta portion of the sunspot cycle. I think you guys are going to obviously recognize that this is a clear trend and, scientifically relevant for, something that happened about 14 days ago, but we'll get in that at the end. Let's go to the next one. 1770. Now, I wanted to point this out. This is the time that they claim there was a very large, potentially larger than the Carrington event. And I'd have to say that the data simply does not support that in any way, shape, or form. You don't see any derivation of the magnetic direction, so the hypothesis they put forward is incorrect. Now, that being said, we'll get to the end of what actually happened in Japan in the 1770s at the end of the talk. Now, let's get to the next one, and you guys will, the big one, the Carrington event. Now, looky here. This is, the only time we've had really modern electrical lines sitting up, telegraph lines sitting around in northern latitudes in Canada, places like that. And quite literally, this was a large enough event. Some people estimate an X20 to an X40, some even higher than that. But definitely was a spicy meatball, so to speak, because it literally melted the telegraph wires in midair because of the, just massive amount of ionized matter raining into the atmosphere. And of course, the auroras were magnificent and just lots of, fun stuff during massive solar flares. Maybe not so fun for modern society, but hey, we'll get into that in some other video. That's, the solar storm of 1859, the huge coronal mass ejection that was Earth directed. Let's go to the next one, 1891. Let's go to the Carrington event and the picture again real quick. Oh, there we go. 1859, the Carrington event shooting up into the, at the low viscosity portion, ramping up. So once again, holding true with the model. Now we go back to, after the Carrington event, we have 1891 and correlation, another low point in the cycle, and a very sharp rise in that one, as you can see. Now going back to this, Let's look at, now take off the other lines. 1898, another huge magnetic turn. And then the correlative data as far as 1898. Would that be the 98 one? Oh yeah, around there. No, that's the big spike there. That would be the 1898, 1900. And if you look, there is 1900, but if you look, the 1898 would be correlative with that blip right there and the little plateau. So once again, the viscosity at the lower points in the cycle being able to build up a lot more pressure and burst forth even on the lower runs and the revving up runs. It's really when you get into the upper peaks that you have the simmering effect and really no chance of coronal mass ejections. So let's go back to the historical data. And the next culprit, take off the isohedron lines or isogonic. What an interesting word. I'll have to look up what that means. 1955. 55, dead on once again. And the pattern is quite clear. Then on to 1960. And you'd think 55 to 60, well, how would there be a cycle in there? But interestingly enough, 55, 60, and once again we have another one of those plateaus, a blip right there where it extended out, which actually correlates with something that very massively happened and kept things a lot hotter and more active on the sun there for a while. So that's, I would say, completely within the model. Okay, on to the next. We've got 1965. Once again, just amazingly spaced very closely, but then 60, let's see. Oh, 55, 60, and then I forgot to mark the 65 on the map. Would be right there with a little star ready to go skyrocketing, so well within that range of those two. I'll go ahead and mark that on the map before I start using the map again to explain this. But here we go, 1975. There is another course correction. Of course, the direction of which way it adjusts the magnetic drift, so to speak, is completely the variable of which way the Earth got shot. You know, if it was a glancing blow to the left, it might, you know, speaking from the sun, let's call the left the north. If it's a glancing blow to the left, the magnetic movement might be more to the left. And that could actually be, now that I think of it, a function of just the sheer magnetization that would occur from some of these events. I mean, you think about a massive electromagnetic strike in an area of the Earth that is highly susceptible to magnetism, or even all the way down to the core with these big blasts from the sun, you would literally get a massive magnetic variance that would start drawing the pull one direction or the other. Let's go to the last one on the model, or, well, the last one on the chart, and they're actually predicting that this will be the place where it is in 2018. Now, if you notice, things have been speeding up, and that's a subject for a whole nother talk. But this is the projected 2018 path. Isn't going to be like this, because we received, about 14 days ago, we received that huge X 9.8 that caused the big quake in Mexico. That was quite a spicy meatball, because it had so many upper M's and X, 3 X's, about 3 coronal mass ejections, and with all that, the Earth really got pummeled. And it wasn't just one blast, it was a series of, you know, striking blows. So that projected path, whenever the actual measurements are done later this year, at the beginning of next year, whenever they update this, in my opinion, should show a magnetic derivation once again, even if it's as slight as some of those 60, 65, 75 ones, it will be there. That being said, it might be, you know, complete directional, you know, shift. And we're not talking about poles flipping, but obviously this is one of the mechanisms by which the Earth does do its flipping on a periodic basis of well, there's a lot of different guesses of what those periodicities are in the poles, but as you can see by the acceleration and the continued increasing, the logarithmic acceleration of these poles flipping, or the acceleration of the derivation of the magnetic movement, you can see that it's been speeding up, and well, all signs point to north, so to speak, or all compasses. Now, that being said, this is basically kind of the model or the understanding that I was really looking at when I started looking at the idea of the viscosity and your real big sunspots, especially at the end of the grand solar cycles. I mean, that is the end of the last 206-year grand cycle, and it is just unbelievably fraught with activity. And as you can see, that activity and these peaks down here, or these valleys down here, are really what ramp up the big 206-year cycle. Speaking of which, I'd be remiss if I did not say that obviously the Atlantic multi-decadal oscillation is completely tied to the sunspot cycle, the El Niños and La Niñas. This is without a question the way it is. So anyone who tells you differently is trying to sell you something. And let's go ahead and look at, this is just the correlative data of the sunspot cycles from back to the 1600s. Once again, all of my raw data will be here in the show notes, and you can take a look at it. Now, here's what my hypothesis would be of why this had occurred in the 1770s in Japan, is that it was more than likely a very large coronal hole stream or a sector boundary crossing. And those two are easy culprits for massive auroras. Now, the idea of seeing the red auroras at that longitude, the idea of seeing those colors at that level of the Earth's, in relation to the longitudinal level of the Earth there, it really is, wow, that had to be real high energy. It does have to be high energy, don't get me wrong. These coronal holes do quite often cause massive auroras in the northern lights and the southern lights, and some, if they're big enough coronal holes, all points in between, because you're talking about a very sharp increase in speed and temperature of the electrons, of the protons, of the alpha decay. Like, there's a lot of stuff hitting the Earth at these massive coronal holes. That's more likely the culprit, even a big coronal hole in conjunction with a sector boundary crossing. And the sector boundary crossing is, of course, this is a pretty good animation, if you will, of the coronal holes as they go around and that solar wind is bombarding out. Well, it's almost like you spend a little bit of time in that dip, and then you go through the peak, and that's when you really get hit with the, really powerful solar wind that really excites particles in the atmosphere, and especially in the upper atmosphere. Now, what would cause red auroras in the upper atmosphere? That's where you get to the presence of iron. Now, as you see here, this is actually taken from a place in Maryland that had red auroras. And what you find here is that this is actually a mining town, a mining district of the country. And so this would speak volumes of why there is heavy particleization of iron in the air over this area that allows for these red auroras. Now, is that the case in Japan? Well, could be, because we are talking 1770s. The Japanese were beginning their industrial revolution in the 1760s, and the shipbuilding regions would be around the Kyoto region, but not any actual iron mining, as I could find. That, as you see on this map here, the iron mining is marked in triangles, and you're looking more on the northern side of Japan, and it doesn't really doesn't, well, if they're doing a lot of smelting, there could be a lot of things, but that really isn't as good as example as what happened here. The Izalco volcano. Yes, a peridot volcano, which is an iron silicate, and quite literally 1770 was the year of its formation. That's when it birthed. That's when this giant behemoth of a pile of peridot burst forth from the ground in the southern region of what is now Mexico. And what you're looking at here is quite literally, they called it the Lighthouse of the Pacific because it was erupting the entire year and spewing copious amounts of peridot dust, iron silicate into the atmosphere, into the upper atmosphere, in the exact same jet streams that would be blowing over that exact same region in Japan. I don't have it marked on the longitude, but as you can see, well within the trade winds, the blowing, if you will, of the particulates. And of course, if you have a massive volcano of that size erupting for an entire year and getting the name the Lighthouse of the Pacific, I'm guessing it was awesomely spectacular. Now, it is entirely possible that this spewing forth was triggered by massive coronal hole stream, sector boundary crossing, but it seems highly unlikely that it was anything to do with a solar flare, because it does in no way corroborate with the historical magnetic movement and how that is a clear indicator of, well, solar flaring activity and massive solar flares, coronal mass ejections. So the thesis in that paper is incorrect, and that this is just something, food for thought, that, well, there are cycles in the sun, there are things that happen, and it's nice that, scientists put forth theories, and theories are great, but whenever new data comes out that obliterates old theories, then they have to be put down, and, well, it was a good guess. So, hats off to doing the research and, well, sparking my imagination to look into this and figure out the whole sunspot cycle, flare magnetic movement correlation, because that is literally, one of the things that sparked me looking into this. So science is really a collaborative effort, and it's good that we can all get together and share our data. Now, that being said, there's a paywall behind the article they put forth, so tell them, Professor Science, tell them how you feel about paywalls.
Professor Science doesn't like paywalls very much. It actually stifles human imagination, creativity, and the forward direction of our entire species. So perhaps we should, get ourselves together and start being a little clearer with our scientific understanding, and not so much
flim-flammery that is going on in the scientific community now with the charlatans that are passed off as scientists today. You know who I'm talking about. All right, well, that pretty much wraps it up for now. I think I covered it. If there's anything else you would like, moi, Professor Science, to look into for you and come up with my own explanation, then hit me with it. Professor Science has a lot of time on his hands, and he's more than happy to learn,
More input.
It's a good thing. All right, well, hey, you won't be able to find it on the site just yet, but you're going to see professorscience.org. I'll have something on there, and shoot, I should probably start a Patreon so I get a little help, with all this science-ification. it would be most helpful, and we'll learn together. All right, well, this is Professor Science signing off. Goodbye.